Thank you, Milutin, for the invitation. I'm very happy to be here, seeing many colleagues. Yeah, I guess you have had a long week already, so it's the last day. And I want to give you a little bit of impressions of what we're doing at the Technical University of Vienna and at the Earth Observation Data Center in terms of exploiting big data tools in order to work with Sentinel-1 data on a global scale. But before kind of go into our technical approaches, I would like to give you a little bit of background on, say, the scientific focus that we are having. So in terms of, we are, say, I'm a physicist by training, so we are very much looking into sensing capabilities, focusing on active microhuman sensing techniques, but we have always specialized on, say, dynamic land surface monitoring, and here on the aspect of the hydrological cycle. So our main variables that we are looking at is, for example, the water content in the soil, water content in vegetation, flooding, wetlands, and these kind of things. Yeah, when you think about what we need in terms of measurement capabilities for improving hydrological monitoring, well, the interesting thing is, well, the water cycle goes now into unknown territory. Some regions are becoming wetter, some are becoming drier, some see more variability, for others it's not that apparent. And the other important thing about the water cycle, for example, is that it's not a natural cycle any longer, but it's heavily influenced by what we human people are doing. And when you think about hydrological monitoring, it's really challenging because, well, it's dynamic. So you need to have a short revisit time. At the same time, if you want to capture anthropogenic activities, you need to have a high resolution as well. And as you want to look into extremes, you need to have long time series. So you would like to have ideally high resolution, high temporal resolution, high spatial resolution, and long time series, and everything in kind of an operational framework. So very challenging.
Oh, sorry, so we're not sharing the screen. So just
okay.
Sorry for interrupting. Let's see. It seems that
many people are online?
About around 10 usually every day.
Это говорилочка, но она вся обгрызена.
Okay, so it works now?
Yes, yeah.
Okay, very good. Yeah, so as I said, we are focused on active microhuman sensing techniques, and at the moment we are say that the two constellations that are important for us are the MEDTOP Advanced Spectrometer constellation. At the moment we have two instruments flying on MEDTOP B and MEDTOP C. And on Sentinel-1 SAR interferometric mode. So at the moment, unfortunately, we only have like one Sentinel-1 satellite up. It's Sentinel-1A, but we are hopeful now that by the end of the year, we're going to see the launch of Sentinel-1C on SpaceX, actually, was decided. And next year, hopefully, then the launch of Sentinel-1D after... well, and Sentinel-1A will be the orbited. So we're going to keep on living with a two-satellite constellation. So these are European sensors, so it's our focus, but the next steps, we also want to go into L-band, so we're looking forward to having nicer data from the US and in the future then from ROSE-L, European. So this is I guess you have many seen this picture, Sentinel-1 SAR satellite really focused on doing the one job of capturing radar imagery, so one long antenna imaging the Earth. So just two examples of services that we are supporting with our research. The one is the global flood monitoring product, which was established now 2.5 years ago. It was a very challenging build-up phase. We do now fully automatic global flood monitoring with Sentinel-1 systematic coverage. And the idea is not any longer that you wait until you get a report about a flood and then do the processing of the image, but you do everything fully automatic so that you process every incoming image irrespective if you know if there's flooding or not. That means if you have thousands of images and there's one image that is flooding, that's what you're doing. You process 999 images without seeing flooding, but then the one flooding you get really very quick, and the users can immediately look at the data without actually ordering them. With this, we make sure that within 6 to 8 hours, users around the globe get access to the data. That part is a part of the Copernicus Emergency Management Service. Scientifically, of course, it's very challenging, because you can imagine that even if you have a really very good algorithm, there will always be a certain kind of misclassification. And if you think that in most cases there is no flood, obviously there will be misclassifications, and users had to get used to this fact that, but once there's a flood, obviously results become very apparent. It's also a very nice product, because we combine 3 state-of-the-art algorithms, one from our colleagues from Luxembourg, from LIST, then from the German Aerospace Agency, DLR, and our algorithm combined in an ensemble approach. And I think it's also very important, we're not just giving to the user our estimation of flood extent, what most people are doing in scientific publication. We also tell the user where we can't give them information about the flood extent. Yeah, that's being provided by an analysis of the historic data archive, saying, well, don't expect any flood information there. Also giving more qualified information, how reliable these estimates are or not. The service was used for the first time in a big way when this huge flood in Pakistan happened in 2022. It started in August, it went into September, and then it lingered on for many, many months with much of the water content. And we were kind of lucky at that time. We only had like one Sentinel-1 satellite, but the orbit, it was kind of nicely overlapping the flooded areas. So you could see the flood progression quite well. So you see individual images, then you can put together like flood frequencies, you can put it together in terms of the first flood detection, and then the whole terrain becomes much more plastic, and you start to understand the processes that are behind it. And now, of course, there's hardly any week passing by without any major flooding, and I mean, from our perspective, I really like this kind of view from above. When you see a certain area where the water is coming down different rivers and approaching bigger rivers. So this is, for example, the flooding of beginning of June in Germany, in Bavaria, where you see here from several rivers that converge then into the Danube, having very high water levels. So it gives you a very plastic view of Earth, actually, that is being often lost if you just have this picture of individual towns being flooded. The other service we are having is the Sentinel-1 surface soil moisture service for the Copernicus land monitoring service. Also there, we process all the incoming images in a fully automatic manner. There we are at the moment still working only at the European scale, but next year we will scale up to global. And we work at a resolution of 1 kilometer. Obviously, with Sentinel-1, we could potentially work at 20 meter, but we are not working at 20 meter because we think it's too challenging in terms of the geophysical retrieval. Yeah, so there's people who give you 20 meter so much estimates from Sentinel-1, but I think actually there's too many effects that are too difficult to handle at that scale, like surface roughness, vegetation, etc., etc. So we try to keep it a bit simpler at that scale, and we do also a lot of pre-processing in order to have like measurements at 1 kilometer that nicely reflect soil moisture dynamics. Also here we give context. We tell users where soil moisture cannot be provided. We give them uncertainty estimates in the other places. Next year there will really be a big update of the service. Maybe just give you an impression of what is to be kind of expected for next year. One of the areas that is really challenging for us is the Mediterranean regions, because there we see not just say on the top of the soil, but we also see deep into the soil. So we struggle with subsurface scattering effects in arid regions like in Turkey, Spain, Morocco. And we had to get these subsurface scattering effects out of it. So I was very happy once I've seen this animation that shows you this progression of dry periods and wet periods and around the Mediterranean region. Yeah, so what have we done to actually make all this happen? So now come more to the technical part. So we need as you see, it's important for us that in the end, it's a fully operational system, but we also need to have always the complete time series. So what we are doing is, if the images are coming in, we are pre-processing them, getting them into a data cube stack. And the data cube stack is what is most important for us scientists. So there we do all the scientific testing and training and model parameterization. If it's now a physical model that needs to be parameterized, or if it's a machine learning algorithm that needs to be parameterized, that's all in this kind of offline processing routine. But once you have your model, you can obviously do the retrieval in near real time. We've also developed a particular kind of gridding system on a global scale called EQ7 that some of you are familiar with. Basically, that activity starts before the launch of Sentinel-1. We tried to kind of question ourselves, can we make what's the best global grid for us in order to not have too much storage space? We basically excluded at that time the UTM projection that is being used by Landsat and now being picked up by Sentinel-2 and also soon Sentinel-1 as an official product, because that was too complicated for us with its 172 zones and very heavy overlap. We also excluded one grid solution because also that's, well, the difficulty of indexing at a very high resolution. So we came up to this continental scale projection. And we went to one and from an azimuthal point of view, equidistance concept that kind of optimizes the trade-off between the size of the pixel and its orientation. The funny thing is now also Landsat, for example, is reconsidering the projection system, going over to a continental scale grid because they also find UTM is kind of falling out of place. The poor thing about the kind of sad thing is they're thinking about an equal area projection, which will mean that they may preserve equal area, but they will have very strong distortions at the edges. So I hope that they will revise the view and come maybe to EQ7 and adopt this as a new analysis-ready data standard. Yeah, and then with having this backbone, we then set up the whole Sentinel-1 processing workflow, where we do all these steps: geometric correction, radiometric correction, try to make sure that noise is being removed, and then tiling it everything so that in the end we have our data cube. We also made the decision that we keep on working at the moment still at 20 meters. 10 meters would have been possible, but then data volumes would have been much higher. So in the end, you see, if you have a 2-satellite constellation, we have in the order of about 380 to 400 terabyte of data per year. So it's now like a manageable data volume for doing the processing at global scale. Still, it's of course a large data volume, and for this we work together with partners from many different organizations to build off the Earth Observation Data Center. It's a collaborative effort where the organizations different organizations pay together to, for example, buy storage. It's connected to the Austrian Supercomputer Center, which is the Vienna Scientific Cluster. We soon also have another supercomputer called Musica that will focus on the GPU servers. And very soon the whole thing will be renamed to the Austrian Scientific Cluster. So it has been developing from a more Vienna local thing to an Austrian activity, which is very good. And we exploit this activity by making sure that what we do in terms of storage is connected to the supercomputing center with very powerful throughput, input-output connections. Yeah, and of course, we have everything that's needed for having services like we do backup on tapes, we do cloud computing for having like an easier entry of the usability, and we use near real-time processing capabilities. And EODC is, of course, just only one of the many platforms that's out there. And many of you will be facing the questions, where do I go to work? Do I go to work on the Copernicus data space ecosystem? Do I go to Amazon? Do I go to Google? And sometimes you may have the impression, well, I need to decide, and then that's it. Then I'm stuck to that site. Yeah. And in a way, also funding agencies behave a bit like this. They, like in order to compete with Google or Amazon, Europe is putting a lot typically in monolithic solutions, as our friends from Netherlands kind of nicely called it. But in the end, there will never be a solution that can do it all. Yeah, you can never grow to infinite size and do everything. In the end, it will always be a connection, like a network of powerful centers that have a certain specialization. And what we need to do as a scientific community, connect them and exploit them in the best possible way, and try not to become dependent, but make a generic access. And say, it has always been at the intention of the EODC that we do this federation. But 10 years ago, it was technically still very difficult. And the nice thing is, thanks to the open source movement, that has really changed now. That's changing now. So I think we are now at what the European Open Science Cloud has proclaimed, the web of fair data and services. I know if you're part of the European Open Science Cloud, it's a very tedious process, lots of policies, but the basic idea behind is great. And this basic idea, I think, is now being realized. So you go from this traditional process, we would see it here in the back, that you first collect data from different places and store it at your own servers and do your own processing there. You have a situation that you as a user have like a slim interface, and from there you can access data at different centers and do proximate computation there. And there's different frameworks. Some of those you have already heard, like OpenGeoHub, that Matthias, where is Matthias? He's sitting there. He's coordinated the project, the Horizon project, the initial one. And but obviously also all the PanGeo supported activities is really important. And I'm looking forward to the next talk about this. So what we are basically now doing is we are taking these open source initiatives, trying and it's always challenging to now know what kind of the best is, but suddenly, you know, there's a standard like Stack. 2 years ago, Stack was, well, do you adopt it? Yes or no? Now there's no question any longer. Everybody does it. So suddenly it's there, you start working. And with this approach now that we want to connect different centers with this open source tools, we also have like a large Austrian activity called Cloudfield Geo, where many different organizations, universities participate, also IASA, also EODC, also the Austrian Med Service. We basically start connecting our capabilities amongst each others, and we start connecting it to the different European capabilities like EGI, EOSC, or what we have, for example, from Copernicus or Destination Earth. And you see here some of the words, like we use OpenEO, we use Stack, we use Dask, all these kind of things. Okay, what does it mean then in your daily life if you have if you want to do big scale processing on different platforms? So we have developed different strategies of scaling to big data volumes on the different cloud platforms. So the first thing is, well, better algorithms. You have an algorithm and you have to adopt it to make it run faster on a big cluster. You can obviously also go to better hardware. The next one you have better frameworks that makes your life as a scientist more difficult, because you first need to understand this very complex framework. But once you're in there, you're in a much more powerful way. And very important tools are Dask, X-Array, ZAR. And of course, then specialized hardware, GPUs. Just a couple of examples. Here we did a global scale correlation analysis at 20 meters. Looking into whole time series. You can imagine how time consuming this computation is if you compare local scale pixels with large scale pixels around. So it was amazing. Our luck was that I have one colleague, Bernhard Ramel, who is geodesist, but then went into gaming industry. So he learned all the tricks of how you get super efficient processing. He came back and now he implemented it. And with this, we could do this this global scale analysis that reveals like properties of the soil. And basically, it's kind of a streaming approach. You download data, you access data, and you process at the same time. So it's a very efficient implementation. Scaling by hardware, obviously, as you go from one supercomputer to the next version, there's also big changes. Also depends on the connections, input, output. Yeah, so sometimes I think you think that the progress can be faster. It's not as fast as you sometimes would like, but it's still, of course, you make progress. Then using open source frameworks. Yeah, I think Dask and X-array will change a lot. Also, I think ZAR file system will change a lot of how we are working. Yeah, and then you have this kind of, you have your workflows. Often, I mean, we always work in Python. And if you optimize it, sometimes we go into C++ for particular cases. Yeah, and with this kind of approach, we try to handle large, like complex physical models or machine learning techniques. Yeah, and the next one will, of course, there we have only started yet slowly, but I think with the Musica computer, where there was lots going to be a very powerful GPU cluster, maybe not so many GPUs. There's much bigger GPU clusters around in Europe, but it will be very powerful because it will have a very fast connection from the Musica disk storage into the GPU clusters. And there we are also kind of looking into ways of how you could speed up your scientific code. Obviously, at some point in time, you might need to go into it and do a recoding of the code for particular cases. But there's also kind of, yeah, simpler ways for doing modest modest speed ups, like from a factor of 2, a factor of 5, to speed up using GPIs. As a last thing, I just want to mention that all these developments we also have been now successfully implementing in teaching. Again, thinking back maybe 6, 7 years, we let our students work on the Google Earth Engine to get acquainted with cloud computing. That's not necessary any longer. We can use Jupyter notebooks in a very powerful way. Yeah. Jupyter notebooks, obviously, it's an effort for the organizations supplying it to the students. But once you have a stable system, it can do everything and more than what you can get on the Google Earth Engine. You're much more flexible in the way how you encode your algorithms, so you can really do everything. And I think Jupyter notebooks are great because you have text, you have graphics, you have code. It's a dynamic environment, so it really helps a lot in our teaching activities. And Theoveen is starting to roll it out to many more courses. So the way how we started is, first we use Jupyter notebooks in a quite simple way, for example, for coding exercises, where it was really just a little bit of coding learning. Then the next step was that we shuffled data from other data centers into the Jupyter Hub, so that there's direct access from the notebook to the data, so that there could be local scale processing. That still was kind of tedious for the teacher, because the teacher always had to pre-process the data, get it on the hub, and then the student could use it. So the next step is that we basically have the Jupyter notebooks, and with these new open source tools, automatically connect to external data sets. Then basically either download the data, which we're still doing with some of the solutions, but the next one doing this proximate computing in this computer center there, if it's working. And of course, then the next step would be that we have these Jupyter hubs, maybe even distributed implementations, accessing the web of fair data. So that as a teacher, you don't have to struggle any longer of predefining what the student has, but it's really maybe often just a line of code, so that students know how to read the data and implement it. And it really has been important for us, because say we were lucky that we have a new studies where suddenly we've had to face 200 new students. Before we had 20, and with Jupyter notebooks we could scale up, and we didn't have to worry so much about this any longer. And now we go step by step from just like teaching activities to bachelor studies, to master studies, to data science projects, scaling up so that it becomes a common framework for lots of what is being done in terms of processing. Just an example, what we, as typical student projects could be now. There's Sentinel-2 data on the Copernicus data-based ecosystem. It's these data being accessed with a software called EODC, open source tool promoted by ESA, developed by a French agency. At the moment, we're still downloading the data, so Sentinel-2 would be lying in the hub. Then there's the notebook. The student accesses the Jupyter Hub, and then they can do kind of all different kind of exercises like processing NDVI, forest classification, wetland classification, whatever. Okay, I hope I wasn't too long. So final thoughts. So we talk a lot about big Earth science data, and I think there's a few studies coming up that really show it. I'm still baffled by seeing how many people still use just 1 or 2 images and then do publications with this. I really would like to see, you know, for example, flood monitoring. Would be crazy if we overcome that situation that people just look at one test site, a few scenes, and that's it. No, please go in different areas, because that really has a big impact on how your algorithm works and how you assess the robustness of your algorithm. So try to exploit what the cloud platforms are offering you in terms of scaling up the work to more diverse environments. We also see that in the next years, I mean, that's interesting for me as a remote sensing person, we see more and more extremely powerful satellite missions up and coming. I'm a bit concerned that the ground segment is not capable of dealing with all the satellites, and somebody needs to take care about the data volume. Yeah, and last but not least, again, a message. I think the web of fair data and services is becoming a reality, and there's no need that you subscribe just to one solution. You can get more, use more of them. Always go to where the best data are. Yeah, and get ready for it. And I think that Hackathon is the perfect actually place for getting ready for this. So thank you very much.
So thank you, Wolfgang. A very nice talk. Yeah, I particularly like the message you passed somehow, you know, like aside, but I think it's super important that, yeah, the EODC and Theo Viana, you're providing a lot of information from satellite data, but you're also providing information where satellite data cannot deliver. Yeah, so when we don't have good observations. Yeah, and I think this is really important message, because like with all AI, we can always provide any kind of information, and AI is amazing. I also using it in my research, so it's not against AI, but sometimes there are simply limits. You know, if there is no data that can support it, we cannot invent the data. It's very difficult, yeah, unless we know something about the object, and so I really like that. Yeah, so thanks a lot. Yeah, I will open floor for discussion and questions. So please go ahead.
Yes, Wolfgang, great talk, nice to see. Also really liked the emphasis you put on federation and sharing resources and working together internationally. I think that's very important. If you look forward, and now with EuroHPC, Austria being in the Leonardo consortium, and also Destination Earth, if you look forward there, how will this improve the current situation, and how much better will become at both forecasting and societal impact analysis, also on flooding, for example?
Well, I think politically it's still a hard way to convince people to go this federation way. So yeah, we as scientists need to prove it's working, and I'm really happy about Netherlands, for example, being in the lead and showing this of how it's being done. I hope there would be like organizations like ESA would better here listen to us to power up on this way. Also, if you think about things like Destination Earth, at the moment, it's also seen that there's like only a few organizations delivering the solution. So ECMWF is setting up these digital twins for climate adaptation and extreme weather forecasting. And I fully buy into this, because basically ECMWF is reselling what they're anyhow doing, going from, say, the 10-kilometer scale to the kilometer scale. And that's what we need. But that's only one component. We basically need to connect to what is ECMWF is doing, and they can only work via federation. Destination Earth is also still very weak on connecting with data. In the end, many people only see a twin as a simulation framework, but where do they get the data get in? That's not happening at the moment. And I think data assimilation may, to some extent, take place at ECMWF, but it will also have to have digital twins, for example, for the land surface hydrology, or maybe digital twin for forests, and they can be in different places. But again, they all need to talk with each other.
Hi, Wolfgang. Here's Michele from UREC. You showed some good examples on global products, but we quite often notice that sometimes these global products do not fit the needs that we could have in areas like we're living in the mountains that do have particular topographic complexity. So what do you think about the need of having, let's say, general global products versus more tailored products for specific regions?
Well, from a scientific point of view, our approach has always been we want to start with a solution, generic solution that works globally, and try to understand the limitations. And once we have a proper understanding of limitations, to make the next step forward. Yeah. So the other scientific approach could be just first think about all the different problems you could have. Then set up the model in this way, and often you end then up to having a regional implementation to kind of limit yourself in a certain way. Yeah, so both things have merits. Obviously, also we learn from local work that tries to look into particular processes, but I think both have their value. Obviously, I know what you mean in terms of complex topography. And for example, measuring soil moisture in complex topography is anyhow a challenge. Like the Alpine environment is kind of a horror scenario for soil moisture retrievals, because if you have dense forests or if you have the shrubs, forget soil moisture. If you have rock, forget soil moisture. If the mountain is too steep, it's also challenging. So I think we should more what we are doing. Yeah, and the most important challenge we had so far in mountainous areas is that you can't do soil moisture if the ground is frozen or covered by snow. And we never had near real-time information at 1 kilometer scale about soil, about snow and soil freezing. Now, we have struggled for many, many years to get ECMWF data into our processing lines. And being a university and not being a med service, we never got it. Yeah, I have been talking for at least 10 years about it. We are just right now, we're on the brink of actually being allowed to use them. And so and with Destination Earth again, well, here I think a big benefit if once the Destination Earth will start running the climate, the extreme weather forecasting. My understanding is that they will have an operational product at 4 kilometer scale that will be open. That will be fantastic. And then we can close a lot of the gaps that we have in mountainous areas, even with the global product.
Wolfgang, so your group published this paper recently, Wasted Petabytes. It's amazing title, and it's provocative, and I think you claim that it's about 33% of extra storage has been used. So can you please tell us a bit about that? Like, how would you change if you were now head of ESA, what would you change really drastically?
Yeah, so the background of this, I already alluded in the talk a little bit about it. The UTM projection system was introduced with the Landsat mission. So it has a heritage of at least 30 years. And at that time, I think it was a very good decision. UTM system is also very good if you just do local analysis, say if you work over one area. But even if, for example, over Austria with its wide east-west prolongation, you already have 3 UTM zones. So obviously you can solve those problems, but there's lots of overlaps with all this. Unfortunately, I don't have now a graphics that shows it, but there's lots of overlaps, and then there's kind of the more you go to the north and south poles, you kind of try to change the gridding system. Yeah, and because it's a standard that was adopted by Landsat, ESA decided to go for Sentinel-2 for the UTM standard. And now, because it's a Sentinel-2 standard, it's going to be also standard for Sentinel-1. So it seems like a 30-year heritage standard comes promoted because it's a standard. So how do you get out of this situation? Very difficult. I don't really have an answer to this. I just would hope that NASA is not adopting a continental scale grid with equal area. I hope they will back up from this. But obviously from EQUI7, we know, again, this overhead, but just working with UTM, you have an overhead of 30% globally. I mean, if you're working in Africa, it's not that much, but if you go to northern areas, then it's really a big issue. And if I have one, you could say, well, is it really that important? Well, for me, if I pay for 1 petabyte or 1.3 petabyte, it makes a difference. So.
And can I also ask you, like, what's your impression of Sentinel-1, which is amazing data, right? But it's quite abstract, right? It's not like optical sensing. So we're not aware what is the potential of that. What is your like rough estimate? How much are we using Sentinel-1 from the full capacity to do mapping and monitoring and real life application? What's your estimate? How much are we using from that potential?
I think with Sentinel-1, first the good message is with Sentinel-1, with this change in the acquisition strategy, there was a real very powerful boost for SAR sensors. We have to compare it with the old situation where we had SAR sensors that had multiple modes. The idea was the space agency says, well, we need to satisfy user requirements. We need to satisfy the forester. We need to satisfy the hydrologist. We need to satisfy the city urban planners. And then they had multiple modes for one satellite because they could do it. And in the end, we had a data archive that was fully inconsistent and incoherent. Yeah, so hardly usable. That was with ERS, that was with Envisat, that keeps on with ALOS to some extent, and other missions. Also, NISA is kind of, could be better, but is already improving. So what ESA was really great, there was some like people like Evert Atzema from ESA saying, now we need to have a systematic acquisition strategy. We do one thing and we do this thing good. And that really changed a lot so that we've seen the number of users of Sentinel-1 going significantly upwards. It also helped SAR interferometry a lot. Having said this, I still think as a community we could do better. Again, people only use a few images. That's in the case of Sentinel-1 still the case because the satellite acquires in the swath orbit and it's not yet giving the data in a simple way, but you first need to pre-post them and put it in your cartographic system. So making a step to an analysis-ready data set that's in a global fixed grid system will be important. And NASA is already leading the way. Alaska SAR facility is showing to do it, unfortunately, again in UTM. But again, it will make an improvement. And I hope that people will start using that capability. And we also see that interferometry also becomes more a standardized processing, maybe not as easy to use, but we're getting there.
So thank you for your talk. It's very interesting about this grid because it's what we all have a problem, even though like that like observation people or people who are making like models on the Copernicus marine services, making the global atmospheric model and so on. So that's I think this grid thing, like right now with the climate digital twin, they understood this problem and they're now using HillPix. So I think that there should be some, not only the satellite people making their own grid system, but that they should communicate with the model people who makes it. What's your and also what's your opinion? I don't know which grid system that NASA is thinking about using, but it's the us is our Earth, right? It's this kind of discussion between NASA and ESA and different international organization thinking about trying to make one grid system so that we don't need to re-grid because we don't want to re-grid. That's why we are using this system. So is there any kind of like discussion going on?
Yes, I mean, obviously that's the big dream of having one global grid system that scales between different spatial resolutions, say from 5 meter to 10 meter, 20 meter, going up to the global scale. I think at the moment we still lack a feasible practical solution. There's still research needed to actually show which one could work in a very fast and efficient way. There's, for example, how's that one called, used by Uber?
Yeah, H3, yeah.
But that's only optimized for doing fastest routes. Yeah, so I haven't seen yet an implementation yet that fully convinces me that we say we do the next step and go away from the continental grids to a global gridding system. If it's there, we would certainly make it. So we at the moment we're also working with ASCAD data, which are much coarser resolution. There we work with a global Fibonacci grids that was designed by ISIMWF. There we already used it. So at some way we kind of say everything that's from 10 kilometer onwards, I think using a global grid is good. We have very good solutions there. Below 10 kilometer, it's getting more difficult.
Thank you.
Thank you.
Thank you for the nice talk. We saw in the latest 10 years maybe a big effort by ESA and Copernicus for openness and fair approach to the use of satellite data, but I can't see the same efforts by other parties. I mean, for all that, for auxiliary information such as in-fields data and so on, which are really very sporadic and only partially available, often closed in some drawers of groups and often also of public parties. What is your view about this big problem? Because it is really a big challenge, having the possibility to make validations and so on for global maps, for instance, and this is a blocking situation for many groups that works on in the research and also for companies in the same sense. What is your view about that?
I'm not sure if you know the International Soil Moisture Network. That was an effort that we, together with GWAX, helped establishing at Wien. And we were lucky that there were in situ soil moisture databases before, and we could build upon this. And supported by this international scientific community, we introduced the service in 2009, and within a very short time, we had many scientific volunteers contributing data to the network. And with this, it was established. Now, after many years of kind of research and further development, it has been taken over by the Germans as an operational activity, still relying on the voluntariness contributions from the different organizations. So I think this example really shows that, say, this open scientific thinking is key to everything, and we even got data from China. And on the other side, we know about state data, like in Czech Republic, we never got because it was policy. So it's really great that the scientific community is pushing that thought and keeping it further. In the end, to make it fully working, policies need to change at each country level. For example, in Austria, I'm really happy, for example, that recently legislation was being introduced so that public important data sets will be released fair and open. And suddenly we have access, for example, to weather radar data that give us a much more possibility to have better characterization of precipitation and the land surface hydrology at the 1 kilometer scale. But in the end, it's hard work. It's legislation. Another example at my university. I'm the dean of faculty for mathematics and geoinformation, and I was able to convince our last rectorate that if you publish data in a fair and open manner, or if you publish open source code, the overhead on the project is only 10%. If it's not open, you pay much more overhead. So it's an organizational incentive to do it, but it must be the political will must be there to do it. Unfortunately, at the moment, I see a bit of a backslash. I see that people start arguing, why should we publish something if the global geopolitical situation is so bad? So it's all upon us actually to say, even if that's the case, we shouldn't be afraid still doing open source and fair data.
Okay, so if there is no, is there any other questions maybe? If not, then I would suggest we move to the PanGeo tutorial.
Thank you very much. Thank you for your question.